Yeah. Hello, everyone. Welcome to today's ASAP seminar. Today's start, we will happy to invite Peter Nordroth to talk about the sparse frontier, sparse attention trade-off in transformer LM. Peter Nordroth is a third-year PhD student at the University of Edinburgh. His research focused on improving the efficiency and transform models. More specifically, he is interested in teaching the models to dynamically allocate compute based on the input difficulty, which can pave the way for tokenized free architectures and more computation optimal model. Let's welcome Piotr to talk about this topic.
Thank you very much for the introduction. Thank you very much for the invitation. Today I'm very excited to present our most recent work about training free sparse attention. This was a long project, a year-long collaboration with other researchers from Cohere, Edinburgh, and Meta. And yeah, my plan for today's talk is to give you an overview of what we did, why we believe it is important, what are our key results, and what are the implications of those results. I also discuss sparse attention and give some overview of the field. So let me begin with simple introduction of why we first need one context processing. So most of our questions, interactions with chatbots usually tend to be a few thousand tokens or something like that. However, at least when I'm coding right now, when I open some large repo, my cursor or any other AI agent cannot take whole repo as a context because of the sequence length limit, because either it do not support it or it's very expensive. So so basically I need to do some extra job and link specific files which are important. The AI cannot do it by itself. So at least to me, it's one of the applications which I think is very important, and it would be very nice if an AI agent could do it. But yeah, current AI models either cannot do it because they do not support long sequence lengths, or because it's very expensive. For example, API from OpenAI costs more money for longer sequences, or from Google, or from both of them. The issue why this happens. So one of the main reasons, not the only one, is the existence of the dense quadratic self-attention mechanism that is inherent to transformer models. So it's one of the reasons that transformers succeeded, but it's also, but we need to pay the price for its expressibility. So during pre-filling, we managed to do a good job with flash attention as a field to minimize memory boundness, but still pre-filling requires the quadratic number of operations, which skyrockets with longer sequences. During the coding, the issue is that we have very low ratio of operations to memory transfers. With GPUs or any this kind of accelerators, we can do more operations. We can do many operations very fast and less memory transfers. And basically, the perfect scenario is to be able to reuse things that we've loaded from memory in many computations. However, for attention during the coding, what happens is that we need to load whole the KV cache, and this all KV cache takes is only used in one operation, which is the dot product. So this ratio is very bad, and yeah, it's an issue. So what we can do about that? Then, like, sparse attention comes in. So the assumption is that we don't need to compute everything. What's at the top is I present two causal attention maps for two different inputs from a single layer and a hat. So the brighter, given part of the attention map, the more important is the interaction between a given query and key. So let's assume that queries lie on the y-axis and keys lie on the x-axis. And basically, the brighter the little square, the more important the interaction. And here, basically, by importance, I mean the attention score after normalization by the softmax. So as you can see, like there are two most important things to take away from this slide. One is that attention appears to be sparse for long inputs, and not every query needs to attend to every key. Secondly, at least for this example, those attention maps are different. So the one on the left can be well approximated by potentially accessing local window by each query token, while on the other hand, the right one has some key salient tokens that should be accessed by every query of the sequence, apparently. So the benefit is obvious. For both preflink and decoding, we can save computation, we can save memory transfers. If we only know which computations we can compute without degrading the performance of the model. On the other hand, the main challenge that we are trying to solve is to figuring out which interactions to compute and which we cannot compute. So right now we are getting to like the clue, the key motivation of this work. I did this archive search a while ago, and basically there are a lot of papers trying to address this issue, this bottleneck. If you look for sparse attention, efficient attention, KV cache, it's 400 papers over the last 12 months, and there are more search terms that would probably also apply to this problem that I haven't checked. And despite this volume, I have checked many of those papers, and for some reason, I felt that there is no yet answer to the following questions, which I think were crucial. And those are, firstly, what are the key differences between those methods? So what is like the design space trade-offs among those methods? With this volume of papers, it's easy to lose track of what are the changes that really make difference, and understanding this, I feel, is critical to guiding future work and developing better solutions. Because if we know what's important, then we as a field will focus on optimizing this part. We'll develop better kernels and continue developing this path, which is the most promising. Next is about the evaluation. So it's very important, I feel, to convince someone to, like a big LLM provider, to use sparse attention, because they really care about the edge cases. As you know, like if someone finds a prompt for which OpenAI model crashes or responds wrongly, then it's a big drama on the internet. So what we care about is actually the robustness. So what I think was missing in many papers on sparse attention is thorough evaluation. And what I mean by that is many non-complex benchmarks focus on tasks such as simple retrieval, such as needle in a haystack. It has become a standard. What I think is that it's not necessarily enough. I think that it's entry level, entry gate. If you cannot pass needle in a haystack, then you cannot solve basically anything. But if you can, then it doesn't really tell you what else you can solve as well. Because I think that this is the easiest possible task. So what I think is very important, what I mean with the second question is how much you can really sparsify those models if you consider a more thorough, a larger benchmark suite which you can control. What is the robustness of those methods? And the final one, which I like to paraphrase as if you should even care about this line of work. And that is if we fix the compute constraints, if we fix the compute, if we fix the setup, what is better to use? So sparse attention, what it gives us, it saves us some computation. So we get a cheaper, a faster model. So it's natural to compare it against a smaller model which is dense. So is it worth it to use sparse attention? And in this talk, I'll try to respond to these three questions. Before we move to the background and before I discuss different sparse attention patterns, give me 2 minutes also to like give you a glimpse of our methodology to maybe convince you that we tried our best to do a good job and that you can trust our findings. So to prepare for this analysis, the first thing we did was a survey of all those methods that were proposed. We wanted to understand what are the differences, what are the advancements, what are the limitations and challenges of those methods. For this, you need to be able to abstract those 400 papers from the last 12 months. So we propose a new taxonomy, and we come up with these 4 key design axes, which I think can be used to describe most of, if not all, sparse attentions that have been proposed. Given that we chose 6 representative patterns, we implemented them in a new repository, which allowed us to like fully control the behavior of those attentions and to be able to ablate the effect of those different design axes. Secondly, about the evaluation. So we also wanted to make sure that the takeaways from our empirical results will be transferable, which will generalize, will be robust. So to do so, what we did, we first surveyed different long context benchmarks and we tuned their tasks, their prompts. We tested, we played a lot with them, but we also checked some prior work which analyzed the cases, the edge cases for sparse attention. So when for what kind of inputs really the sparse attention is stress tested. So among others, we found that this, for example, happens for synthetic inputs. Some prior work has found that the latent representations of model representations behave differently and form different manifolds with synthetic inputs which lack semantic meaning, and basically they behave differently than natural inputs and make things more difficult for sparse attention. So we also tried to do our best to include all types of inputs for which attention as a module behaves differently, so like different types of tasks, as well as include different characteristics of inputs, such as whether this is a natural a question in natural language or is it a synthetic input. And secondly, of course, we run a lot of experiments. If I'm not wrong, contrary to prior work, for example, we have evaluated also larger models, which was a bit complicated, but it was like mainly a technical issue that had to be solved. But we evaluated, we controlled for those variables in our experiments, whether it was sequence length, it was model size, it was sparsity level. We want to understand the effects of those variables that they have on sparsity and how they react with different methods, which I think make it the largest scale empirical analysis to date of training-free sparse attention methods. Right now, I'll start with the background and discuss something about sparse attention, how it's built, how we can design one. But also a quick note, if you have any questions, feel free to ask during the talk, feel free to interrupt me. I don't have any issues with that. So, like I said earlier, the main issue with approximating sparse attention is that every sequence is different if every sequence has different patterns and relations between the elements of the sequence. Therefore, the sparse attention behaves differently. So these attention maps are very irregular. They differ across tasks, models, layers, and heads. And the key challenge of sparse attention methods is to adapt to these dynamics and figure out on the fly which subset of interactions to compute efficiently. I'll use the example of two state-of-the-art methods for training free sparse attention to go through the key design axes that we have distinguished in our work. So starting with units of sparsification. These category, this axis, relates to what structural units a given sparse attention pattern computes or neglects. So based on our literature review, we can distinguish two main categories of methods. One is the one which splits the attention matrix into smaller blocks, chunks or tiles, let's say 64 by 64, and selects which to compute. On the other hand, the other family of methods called vertical and slash focuses on columns and diagonals as base units. So these choices reflect, I would say, different bets or different assumptions on where the most important interactions lie. And these are often based on empirical observations, empirical evaluations. For block-based methods, we assume that if some interaction is important, then it's also worth it to compute interactions in close proximity. On the other hand, the vertical and slash methods rather believe that there is some set of critical tokens that are important and should be attended by the whole sequence. So if one token is attended, then it's attended by all the queries. Next, next we have importance estimation. So once we have decided which units to keep, to choose, we need to have a way to somehow assess them, to rank individual units with some importance measure to assess how important they are, how important they will contribute to the output. So in terms of block sparse methods, the importance of each block is estimated using heuristic block representations. That could be, for example, average token representation in the block. Then, using those block representations, we can compute the dot product between blocks, and this way we would obtain some estimate of the attention scores aggregated from the block. This is, of course, heuristic. On the other hand, for the vertical and slash method, for each column, so like each key token, and each diagonal, we accumulate attention weights from suffix tokens. So what happens is that we would compute the attention scores between the suffix queries and all the keys. And then for each key token, we will aggregate the attention scores it received from the suffix tokens. What matters is that those are two different approaches to estimate the importance of those base units, which we call units of sparsification. And in both cases, we end up with a numeric importance score for either every block or every column or diagonal. Next, we have the next axis, the budget allocation. So with regards to that, so what we have right now is a set of units which is manageable, and for each unit we have its importance score. So I believe the most naive approach right now is to choose the most important units. But the question is how many you should choose. So you sort them and you choose the top K most important units of sparsification to compute, and the rest of it are skipped. So the less we choose, the less we compute, the greater the sparsity, and hence the greater the speed up. These two methods that we're discussing here, dot sparse and vertical and slash, both use fixed uniform budget. So it means that for every layer and every attention head of the model, the same number of units is kept and computed. However, it's important to note that there are methods, and it's not very hard, which allow you to adjust the budget based on the input, and for example, for the layer of the model. And this adjustment is based on some estimate on how about the entropy of the attention distribution. We also evaluate those methods in our paper and ablate the effect of this adaptive budget allocation. And maybe we'll get back to that later. Now, let me discuss the results. I will further discuss the effects of those design axes that I've just gone through, but I thought that maybe it will be more interesting to do that based on some real empirical results. So these three are the highlights from highlights of the results from our paper. And firstly, that is that no universal method exists yet, and these are task dependent, and there are many design-related trade-offs which are not easy to solve. Also, right, mainly among those axes that we have just gone through. Secondly, generally very high sparsity, over 90%, is tolerated on average. 90%, skipping 90% of operations means that you can achieve 10 times speed up of the self-attention computation, which I think is enormous. So on average, I think that things are very promising. Although what is very important to note is that high variance is observed, and we observe that some types of inputs are particularly sensitive to sparsity. We'll discuss it why, and but in general, this requires very careful deployment if we really care about the robustness of our model, and robustness, and about the robustness of its performance when deployed with sparse attention. And thirdly, we do the analysis where we fix the compute cost, we fix our setup, and we find that indeed large sparse models are better than small and dense ones. So I'd like to start with further continuing talking about the trade-offs between different sparse attention methods. But yeah, first thing about the evaluation. So among others, we evaluate those patterns that we have picked, some representative sample of patterns, on single question answering tasks. We picked 3 natural language QA datasets, and we construct the input in such a way that samples from those datasets are pairs of document and the answer, and we stack many documents, possibly unrelated to one another, and then we add a question, and basically that's it. So we stack the documents until we reach some sequence length. This, of course, creates a scenario where in a very long input, only a small part of it is relevant to the question, because the model could only focus on the question, on the document that was associated with a given question, and that's it, and that's all what it has to retrieve. What I wanted to stress here is that for these type of tasks, which rely on retrieving and reasoning over a very concentrated, narrow piece of information in a very long input, we can introduce a lot of sparsity and nothing will happen to the performance. Here on the x-axis is the attention compression, which is the inverse of the sparsity. So 20 here on the far right of the x-axis means the 20 times compression of the attention, so 95% attention sparsity. So with 95% attention sparsity, we maintain basically perfect performance across these single question answering tasks, which I believe demonstrate that there are tasks which are particularly okay with sparsity. And if we care about for evaluation, we should be careful not to be biased by those, because for these easy tasks, a lot of things just work. On the other hand, in terms of more difficult tasks, in our paper, we also evaluate tasks which are multiple question answering, so many questions like previously, multi-hop questions, and information aggregation. Let me start with the plots at the top for multi-question answering. So because it's the easiest and the most intuitive, I feel, example to give to kind of illustrate what's happening. As we saw on the previous slide, when we have only a single question, to answer this question correctly, we only need to focus and retrieve a single document for a very long input. And it feels like a perfect scenario for sparse attention. On the other hand, if you construct the input in exactly the same way, but then at the end, you ask multiple questions instead of only one, then you need to retrieve as many documents as you have the questions. So on the left, we have 4 questions, and on the right, we have 16 questions. And basically, the performance decline correlates with the number of questions that we are asking the model to respond. And I think that in this case, the explanation is very intuitive, because with more questions, we have more relevant tokens to which we need to attend, which we need to process, which naturally implies smaller sparsity. So if the attention is more diffuse, less sparse, then when we start adding some compression, we start adding some sparsity, then at some point, possibly earlier than before, we will start missing some important things and our performance will go down. Secondly, for multi-hop and information aggregation tasks, so these are a bit harder, less intuitive to reason over in the same way, but generally the same logic applies. To solve these tasks, we need to retrieve and reason over multiple parts of the input, which again naturally would imply less sparsity. One very critical takeaway from this slide, which I wanted to make, which I'll discuss in the follow-up slides, is that please note that among these two methods that I have introduced earlier in the presentation, so one which relies on verticals and slashes, and the other one which relies on blocks. The one which relies on verticals and slashes works better, significantly better for multiple question answering, while on the other hand, the one which relies on blocks works better on the other types of tasks. And this is because for more difficult tasks, which are not single question answering and requires concentrating on a very small portion of the input, the attention maps, again, are very hardly predictable and display different patterns for different inputs, for different heads, for different layers, for different models. They are very hardly predictable. And assuming that there are these two categories of methods, then one is naturally more suited for one set of tasks, while the other is better suited for the other attention patterns. And yeah, and this is a trade-off. And what I think is very important right now is to note that training free sparse attention patterns are very much challenged in a way that they are given a model that was trained with dense attention, and their task, their challenge is to be considered robust, to be able to approximate all the attention for all possible inputs, to be able to cover all those edge cases for different inputs, for different layers, for different heads. I think that this is very difficult. So while one question you could ask here is, for example, like why different attention maps emerge for different inputs? I think that this is a very interesting question for interpretability work, but in context of sparse attention, I think that we should just accept that those different patterns emerge, and we should instead think what we can do. Is there anything we can do to be able to cover all those edge cases, to be able to say that our sparse attention method is robust? So what we can do? I said that there are two families of methods, one which relies on blocks, one which chooses individual tokens and individual slashes, and then those are shared among all the queries. These seem completely different, and these may also seem unnecessarily complicated. I mean, why blocks? Why keys? Why diagonals? Why cannot we just compute top k token to token interactions? At least based on like these attention maps, you can basically not compute 80% of this matrix. Why cannot we just focus on the yellow parts which are important? So this is probably one of the most important slides. The explanation of like what is the main limitation in the design of sparse attention methods, which are training free, is that the cost of the dense attention is quadratic. That's what we are trying to avoid. For sparse attention, the total cost of the attention is the sparse computation itself and the cost of figuring out what to compute. So that's many papers call that index building. If we compute k interactions per query for n queries, then the cost of sparse computation is n times k. If k is fixed, let's say for every query, we will only compute the interaction with 256 keys. Then basically k is a constant and we get linear attention. So that would be amazing. However, what we also need to do is to figure out how to estimate what to compute in less than quadratic time, because otherwise it doesn't make sense. And specifically, what we cannot do is to estimate the importance of every query key interaction, because that would require n-squared computation, because we would need to produce some importance measure for every query key interaction. So it's not only about the sparse attention computation, it's also sometimes computation itself is way cheaper than actually understanding what the pattern is and what we need to compute at a given moment to minimize the impact of the approximation. So this table shows which sparse attention strategies are actually computationally feasible. So we cannot compute it individual to individual because it would require quadratic number of estimations. What we can do, so these two methods that I have presented earlier, is we can potentially estimate which individual keys to choose for all the queries. And we can do that either by sampling queries and then estimating importance of different keys, or taking the suffix of the queries to estimate which keys will be important, and then share these those keys among all the queries from the input. We can also compute chunks of queries to chunks of keys. Why this work? This works because here I also mentioned the estimation cost of those methods. So if we compute which chunks of keys we would like to attend for every chunk of for every query chunk, then the estimation cost of such an operation would be original n squared divided by the chunk size or the block size. So if we think about the block size of 64, then it's computation which is 4,000 times faster than the dense attention. So if you only do it block to block, then this estimation cost becomes negligible compared to the dense attention, which makes it feasible. On the other hand, we cannot do individual queries to individual keys. We also shouldn't be able to do like split into chunks of queries to individual keys, because then the cost would be n squared divided by the block size, which might not be enough, but maybe for some applications for very long sequences it would be. So by this, what I'm trying to say is that these two approaches that I have shown here really are the effect of this trade-off. So we can either do it block to block, and we can allow for extra flexibility of allowing different query tokens to attend to different keys, or we can choose individual keys, individual tokens, but we need to share them among all the queries, because otherwise we wouldn't be able to estimate the cost of different units efficiently and compute the sparse attention efficiently. And as an effect, those methods are not perfect, because sometimes one pattern is needed, sometimes the other pattern is needed. And that's why we are still looking for something in between, something that would satisfy the requirements of all variety of inputs and at the same time is easy and efficient to compute. Coming to the second result. Here, what we did, so we demonstrate the results across different model sizes for different sequence lengths. For every combination of model size, sequence length, and the task, we calculate the maximum compression that we can apply to the attention without degradation. And you can think about that. What is the maximum compression we can add to the model without the performance on a given task going down by more than 5%? But we employed more sophisticated statistical framework to do so. There are three takeaways from this analysis. Firstly, on average, really very high attention sparsity is tolerable by the model while still fully maintaining the dense model performance. And this on average goes beyond 10x. So 10x for longer sequences would basically mean increasing the throughput by 10 times, which would be amazing. Secondly, there is no clear impact of the model size and the sequence length on this statistic. We can discuss. I can discuss this the intuition behind that if that's interesting. Otherwise, it's also described in the paper. And thirdly, what we observe is that variance is really very, very high. So you can guess that here at the top, the tasks which tolerate a lot of sparsity are tasks which can be considered somehow easier or just demonstrating higher sparsity. On the other hand, it's very important to remember about that there are tasks which naturally are less sparse, that require aggregation of information from different parts of the input and processing of different parts of the input in such a way that these sparsity just do not exist in such a way as in some other simpler tasks. So it's just a call that it's very important to thoroughly evaluate the sparse attention methods, because there are inputs which are definitely more sensitive to sparsity than others. And now coming to the final result from our paper. So we'll be comparing large sparse models to small dense ones. The question being, given the same computing budget, is it worth to use sparse models instead of dense ones? So again, I think that this is a crucial question, like the first that you should be asking, because as every efficiency method, sparse attention trades model capacity, model quality for better performance, for better efficiency, for being faster. So there will always be like this trade-off. And if we apply sparsity to 72B model, then it will be cheaper. But is it worth adding it? Is it worth using it in such a setup? Or would I be better by just using smaller and dense model? So we fix the compute on the x-axis. In both setups, what we do, we present here the average performance across tasks at 128K sequence length. We presented across these four different model sizes for many compression ratios from 1 to 20. So 20 compression ratio means 95% sparsity. What we can observe is that on the left, we have the results for prefilling, and on the right, we have the results for decoding. what we can observe, yes, and we use two different measures. On the left, we use flops, so like computations, which is the main bottleneck during prefitting. During the coding, we use memory transfers. And it's also very important to note that here I include as the cost of the model, I include all the model components and not only attention. So it's not like I'm saying that sparse large attention is better than smaller dense one. I'm including all the other operations such as feed-forward layers, unembedding, logic projections, and things like that. So I use these two different metrics, but I believe that these translate into actual walk work time that you would measure with optimized implementation. And the takeaway from this slide is that sparse methods in fact lie on the Pareto frontier, and that it is better to use a larger model with sparse attention for longer sequences than using smaller and dense ones. And the effect of adding sparsity to the model would even be more impactful for longer sequences in the future. And to conclude, the three questions that I started with. I believe that no universal method exists yet, and tried our best to illustrate the differences between those methods and the effects of different trade-offs that the design of sparse attention method introduce. And I'm looking forward to seeing how it evolves in the future research. Secondly, how sparsity can use to maintain their performance. I think that a lot, and I think this is very motivating. Being able to speed up models 10 times would be amazing, would be a great achievement. Both during training and during inference. It would save a lot of money. But I also make this call to be very careful and to definitely use to thoroughly evaluate whatever you're deploying and just consider like paths of different difficulties. Consider far end, because with training free attentions, you don't really get theoretic bounds for how your model would behave and how it would generalize. So thorough evaluation is very important. And finally, we find that sparse models are more effective. And most of the frontier LLMs nowadays have some form of sparse attention, although usually very naive local window, sliding window attention. And I expect this trend to continue. I think that more models will employ sparse attention, and I think that with time we will start deploying more sophisticated sparse attention patterns. Finally, I want to advertise that that we have released two repositories for sparse attention. First, the one that we use for this project, which you can use to evaluate new patterns or the existing ones, and the other educational one, which I implemented 6 months ago for the NeurIPS tutorial, which I think is a perfect starting point before diving into optimized code if you want to learn more about sparse attention. And that's it. Thank you very much. Let me know if you have any questions.
You feel free to ask any questions that if you have some. Yeah. Yeah, I think I have one questions because that I think from your result it seems that also from the previous work that vertical slash is a very important property of the sparse attention, but many people also mention that this is maybe something caused, especially the slash ones that they are something caused by the rope embedding. Do you think this is a good feature or bad feature? Yeah.
Sorry, so what property?
Just the vertical slash pattern, yeah, especially the
Mm-hmm.
slash one, yeah. And people gradually find that the slash is caused by the rope embedding, yeah, because
Mm-hmm.
yeah, it is a fixed position embedding. And as I just curious about, do you think this is a good feature or a bad feature? Because that I think for vertical one, we are easy to understanding that because there are some important tokens, yeah. But for the slash one, it seems to be some bias of the rope embedding that force this token to be important, yeah.
So yeah, I followed this discussion and I remember that friends discussed this. And my best answer to that is that it could be the effect of rope embeddings, and I could imagine some hand wave explanation that tokens attend to some tokens at some particular distance and like transfer information between chunks, and this might have been caused by some form of positional embeddings, um, and we adapt to that. I think that this could be the case. I don't have a clear opinion whether it's good or bad. What I think that maybe it's not the best way to not the best question, not the question that we should be asking if we want to push the sparse attention field forward. Um, because what I mean by that, this is an amazing interpretability research. Recently, there's been paper why attention sinks emerge in transformers. Also, I believe that soon someone will provide better understanding why those slashes exist in
Yeah.
dense attention. However, I think that what training free attention do, uh, and I think that this is very, very hard. They are trying to adapt to what was learned by the model with dense attention during pre-training. And I think that this is a very hard job because you really need to be robust to all the different scenarios, all the different attention maps that emerge, all patterns. You need to understand, you need to spot them, and you need to be able to accommodate for them. On the other hand, I really think that the future is actually trainable approaches. So like the approach from DeepSeek, the native sparse attention, or dynamic memory compression, or dynamic memory sparsification that we have developed with NVIDIA. I think that by biasing the model and telling the model that, okay, you need to use sparse attention, then some other patterns will develop and we will no longer need to, like empirically figure out what is happening in the model, what is happening in attention, how to best approximate it. Instead, we will tell the model, okay, you need to be sparse. And I think it's a better way to do that because then you don't need to like be reactive, you're proactive.
I see. Yeah, this makes sense. Yeah, but some people that they told me that at DeepSeek maybe they gave up their native sparse attention because when they try to scale up or do something, it do not maybe works very well. Do you think that for the trainable one, that for the future, that I guess that maybe something should be start from the post-training instead of the pre-training? Because I think one problem is that it's really hard to collect so much long context pre-training data. Yeah. So, for example, if the most data is 4K or 8K length, that it seems not very useful to add sparse attention in the pre-training. Yeah.
Mm, yeah, I completely agree. So like, for example, like when Quen released 1 million context model, they do not turn on sparse attention for sequences that are smaller than 64K. Because like, what's the point? For those smaller sequences, flash attention is very fast, so we don't need it. Like when the time we need sparse attention is when we go to 1 million context. This is the issue. So I agree with you.
I see.
So, so generally, I think it makes a lot of sense. At the same time, compression inherently it seems to be like very, uh, very hard task which people were trying to solve for a very long time. I mean, to like zip compression, all kind of compression, and we are also trying to kind of do the same. We want to compress KV cache. We want to save computations. Um, I completely agree with you that we lack good long context data. Um, and I agree with you that um, sparse attention is important mainly for longer contexts. But um, those longer contexts, although it's like, I don't know, 5% of real user queries, those are still very important to progress the AI further. And we need to do something about that to be able to accommodate for them. And maybe it makes sense. So I think that not necessarily we need to employ it to pre-training during SFT when we have this high quality long context data. Maybe it's enough, but what I'm thinking about is that we also need to develop a sparse attention method which is sample efficient, which can learn from only a few hundreds of steps, which I think is another challenge.
Yeah. I think this makes sense. And maybe one more question is about because I see that you have tested on so many benchmarks, and because that many startup or many just industry people they just try to propose some new long context or sparse attention method. Do you think that current, for example, the long context benchmark they are strong enough to evaluate the model's true behavior on this long context? Because that, for example, previously I tested Llama 3 and I found that although the Llama 3.1 although they claim that they have 120K contact length, but but one very interesting I have noticed is that if I use full attention, you can see maybe the productivity drops that after 8K which is their extended length. But if you use some top K attention or some block sparse attention, that the K at change just means that the model cannot accurately identify what is important at the 8K. They have given me a concern about whether currently long context models they are really long context, and this may result in some performance drop for the sparse methods. Yeah.
Yeah, I completely agree with you. That's like we spend a lot of time like figuring out like what should be the good benchmark because that was the main thing that I had issues with when I was reading different papers is that they were claiming very good results and sometimes I just wasn't believing them in completely because they were testing like needle in a haystack, which is the simplest possible task. Um, so I think that good benchmarks with properties that you mentioned, such as like if I test on this benchmark and the performance will not go down, then it means that my sparse attention method is robust. Uh, I think that it would be amazing to have something like that. And we are currently working on a benchmark like that. And
Mm.
my best, um, and I think some advice to others just to be diverse. And I also think that the benchmark suite that we have developed and we release publicly in this repo for testing sparse attention is okay. So there we include 9 different tasks, which are, I think, diverse enough. Those include both natural language, synthetic inputs for different task types, and I would recommend using this one until we develop the benchmark that we are talking about, and that would be that would check all those boxes.
Yeah. Looking forward to it. Yeah, I just think that maybe sometimes sparse attention, just maybe for example, sometimes the sparse models they do not perform very good. Maybe sometimes the problem may lies in the sparse pattern, but maybe sometimes it all can also lies in the long concept ability because I think full attention is too robust because it can see everything. Even you have some not very accurate attention scores, and still maybe you can retrieve many information. But when it comes to sparse attention, I think things will be changed. Yeah.
I completely agree with you. Like to be able to do sparse attention, like the constraint for it, the requirement is to be able to do long context because you need to know which interactions are important. And for that, you need to be able to do long context. So I again agree with you completely.
Yeah. This makes sense. I think these are all my questions. Is any other audience has some more questions?
Yeah, I had one other question, Piotr. Great talk, by the way. I was thinking about what you're talking about, where you had the kind of limit on how much attention was needed, and you saw that within these different sparse methods. I was curious, did you guys do any kind of attempt at checking that inefficiently? So just saying like, do how many um perfectly selected tokens do we actually need to attend to? Like if you're using direct top K, even if it's inefficient to do it, did you ever check to see kind of what percentage of tokens were needed for these tasks without relying on any special block or vertical slash type of formulation?
Yes, with it. Thank you for your question because I'm very excited about that. Shortly, what we did was basically what you said. So checking what's the maximum sparsity we can achieve while still being able to solve a given input. If time doesn't matter, if efficiency doesn't matter. So what I did was taking inputs and outputs and um, computing the gradients with respect to the output. And then I would compute the gradients with respect to the attention scores at each layer and each head of the model. With those gradients, I was able to estimate what would be the change in the loss if I mask a certain interaction. So yeah, I just considered all token-to-token interactions, individual ones. I didn't care about efficiency at all. So I tested these. And I also employed like a training where on a single example, I was training masking variables that would mask certain tokens. So I was actually like training the model to figure out for itself how much tokens it can mask. I was maximizing, preserving the performance and also the sparsity. And I achieved better results than those limited methods. Um, how much better? I would say like crazy better. Um, I would say crazy better, like 99% sparsity sometimes. Um, Although with this methodology, there is one issue. And the issue is that you're not always sure whether the model is not tricking you, because maybe sometimes if you mask two important things and then leave something noisy unmasked, then maybe the output will be still the same and the model just learns to trick me to maintain the same output while masking 99% of the input, which often happens like if you frame the reward poorly in reinforcement learning. So I account for that, although I think that in general, like I was getting great results and there is more sparsity definitely out there. However, uh, having said that, I think again that in the future, this is the I don't like this approach. I don't like this approach of adaptation. I don't want to adapt to every possible scenario because I think that this is too difficult. And instead, I'm a fan of trainable attention when during training, we tell the model, okay, all you've got is sparse attention. You need to be sparse. You cannot be dense. And instead of adapting, then telling the model explicit constraints.
Yeah, that's interesting. Well, I guess I had one other question, then a follow-up. the other question was, so in addition to that, did you also try these benchmarks on your, what should we call it, on your inefficient sparse attention?
No, I haven't, because those were too expensive. So I
Okay.
was just testing individual inputs, and I was
Yeah, it would
just
be interesting
uh,
to see what percentage, because you said, you could get like an average of say 12 times sparsity. I know that it was very variant. So some of them maybe you could only get 3 times sparsity, and some of the benchmarks you could maybe get 20 times sparsity. It'd be interesting to see what that range, the difference in that range would be with the perfect inefficient sparsity, just to know, like, it gives you like kind of like a lower bound or something, or rather an upper bound of how sparse you could get for a given benchmark. So it'd be
I
very
completely
interesting to
agree.
know that relatively to the amount of sparsity achieved successfully with, say, block sparse.
I completely agree. Like the issue is that it's very expensive. Like I said, for a
Yeah.
single input, I was doing entire like training procedure, so it's very expensive. I didn't have compute for that, but I agree that like having access to such an upper bound would be crazy, crazy information to have to develop a better one.
Is there a reason you could, I mean, you should be able to do it with just regular attention and taking like a top K, right? You don't need to train a whole new model in order to do that.
I mean, so what I meant was, um, if you rely on the attention scores, the signal what to keep. So one method in which you test the upper bound of what is achievable without caring about the efficiency is like computing the entire attention map, computing all the attention scores, and then selecting top K, right? But this is relying on the attention scores. So what I've also tried, what I was describing, is we weren't relying on the attention scores, and instead with this gradient approach, we instead relied on the model output, so the change in the model output. Because sometimes you can imagine that some token receives 90.9 attention score, but it wouldn't change the output. So we both tested what happens if you look at the attention scores, but attention scores is some proxy for how important the token is, how important interaction is. A better proxy is actually using the change in the output, the change in the loss, to assess how important the interaction is. And for that, you need a backward pass. And if you want a better approximation, then you want smaller learning rates, so you don't want to do it across multiple training steps, and that's what made it very expensive.
Gotcha. Makes sense. Yeah, to address your other discussion point about the training from scratch versus adapting an existing model to use sparsity, we've been there. I don't know if I have like even in my own head an answer one way or the other, but we've been doing a lot of work doing what we consider conversion, but basically distilling attention-based models to either not linear or recurrent forms, or also to other forms of attention. And it's been interesting because it's been really successful. So that kind of points in I mean, I kind of think of linear attention or compressive state forms as just a different variety of sparsity in some sense. And so it indicates that there may be some ability to, post-train these attention maps into a different kind of a form afterward. So we've been doing it with large models like Qwen72B, and getting pretty good results. I wouldn't say the results are all the way there yet. And one of the things that we've been having issues with is some context length usage ability, especially as you get to the more complicated kinds of benchmark tasks. But it's been interesting that that it's possible to kind of rapidly do this sort of conversion, because it points to the direction that it might be possible to kind of learn some new interpretation of this stuff after the model is already trained.
Yeah, I completely agree. And please let me self-advertise with that. I'll try to share. Okay, so this is the work that we have released with, like, as like a continuation of my work from an internship 2 years ago, but it was then picked up by my advisor from NVIDIA. So we basically take pre-trained models, and in a few hundreds of training steps, fine-tuning steps, we teach the model to evict tokens, which basically leads to sparse attention. And we test it on reasoning models, and this works very, very well. And it sounds like, yeah, very similar to what you're saying. And I really like this approach. It's like a follow-up to the version we worked on like 2 years ago, and this one works like 10 times better. Yeah, also if you're interested, check this out, because I like it, and I think that it's a good work.
Cool, it sounds amazing. What's the name of that paper?
It's inference time hyperscaling. I sent it to the chat.
Oh, okay, great. Thank you.
I have a question, maybe not directly in the context of this talk, but I'm thinking, like the origin of attention, because when we train the model, our loss function is next token prediction, right? But then when we solve a task, it becomes a task-dependent attention. Maybe not. Like intuitively understand, like for example, coreference resolution, right? We want attention into references. Would it emerge automatically from the prompt? And basically, what's the potential of all these different task-related attention in this generic model? And then, if we are talking about sparse attention, we would be interested in specific solutions. I don't equate attention, maybe we should, with the result on any particular task. But maybe it's still it feels like it's important, like for coreference resolution, to kind of have attention between references, right? But maybe it's not necessarily to produce good result of the task. Maybe it's like too shallow reasoning. But anyways, in the context of particular task, if you're talking about sparse attention, maybe it means something different than sparse generic attention. What's your take on it?
So I have some understanding of your question, and let me know later if that makes sense. So the way I'm thinking about that is, you mentioned like this specific example of coreference resolution, and I agree that in such a case, being able to look at all the references is crucial. And I'm not debating that. What I think, on the other hand, is that if you ask a coding question, then you potentially put in your context 20 different files with 20 different functions, and you want your model to correctly help you with coding. And these 20 different files contain 100 functions, which then translate into 100,000 tokens. We have a model which is 80 layers, and at every layer there are 64 attention heads. What I'm saying is, that sparse attention assumes that not every query has to look at every key, at every possible layer, at every possible attention head. Maybe for coreference resolution, you need to only look at the other references. Maybe for coding, you only need to look at the tokens that correspond to the function you're in. And that's it. And maybe you don't need to compute all of it. And I not necessarily see this as a limitation itself. If we come up with attention method which is dynamic, which correctly identifies which key tokens are important for specific query tokens, then I see no issue with that. But let me know if I understood your question correctly.
Yeah, I mean, I'm just, sorry, it's not a very clearly formulated question, but basically, there is a kind of it's like a tension between two purposes of attention. So, one, you get like a generic attention with all these layers and all these attention heads. Uh, Presumably, it is universal in terms of it could serve any task, right? But then when we are talking, and again, it's also changes, right? Depending on the on your query, or it doesn't change.
Yes, it changes.
So it's also it's a kind of murky issue. But then you in the context of particular task, for example, just an example, co-reference resolution. And you are totally right, we just need a very specific kind of attention between references. And maybe it's already somewhere within, so maybe it's hidden somewhere within this model, or maybe it's already explicit. It's one of this assortment of all possible attentions with all possible heads and layers, right? So, but what we are doing is sparsifying attention, right? We're kind of we're doing it disregarding the end task, right? We just hope we specify. We don't like different tasks could suffer different consequences, or maybe not.
Oh,
So that's what I'm saying. How to look at all this thing, like assuming, and again, I'm not sure that it's 100% correct, assuming that for a task you need a specific attention, like for co-reference resolution, you need attention between, and again, it's a kind of dynamic because it depends on the pretext, on the query, right? Assuming specifying and how we make sure that we don't damage this particular, artifact that presumably is already there. So that's
sure.
Yes.
So I think that's one of the most exciting challenges for the next for the sparse attention, because in this figure, so what we presented here, like those individual dots here, those present different tasks at different configurations, and each dot represent at which sparsity level the performance degrades. Something happens to the performance, something statistically significant. And yeah, I wanted to stress the importance of this variance, right? So this variance is enormous, and for certain tasks we can have huge sparsity, for others not. And what I think is still not solved and not addressed yet is dynamic budgeting and further dynamics of these attention patterns. I agree with it. So if I understand that correctly, you're saying that what can we do to make attention more dynamic to accommodate that different tasks are harder or easier than the others? And for some tasks, potentially, we cannot accommodate sparse attention. And we should be able to identify such tasks. And I think that that's a challenge, because right now we cannot do it automatically, robustly, because given this plot, someone would just deploy a model with 90% sparsity. It would work generally okay, but some tasks, maybe cross resolution, maybe something else, would be affected. And it's a great research question for me, to be able to identify how hard the given input is, how hard the given task is by the model, and then by the model itself decide what should be the sparsity it employs for a given input to be able to solve it.
Yes. Okay. Thank you. Yes, also like where is attention localized, it's like also random because it depends on the random initialization, right? So it's a kind of complicated issue. Every time it shifts, depending when you train model, initialize it differently. But in general, like it's like mechanistic interpretability issue maybe. Thank you. Yes, I'm just. But in general, does attention really change in terms of what heads and layers are employed depending on the task query or not?
Yes, definitely. Yes. You can check out the references from our paper. So we make many references to different studies which show how this differs.
Okay. Thank you. It's very interesting.
Okay, shall we finish now?
Yeah, I think if there is no more questions, we can finish now today. Yeah. Thank you very much for the great presentation today.
Thank you very much for the invitation.